All right, let's go. Yeah, so we should distinguish between scalar and vector quantities. Give examples of each. Use scale diagrams to find the resultant of two vectors. Calculate the resultant of vectors which are parallel, antiparallel, and perpendicular. Explain that a single vector is equivalent to two other vectors at right angles. All right, so we'll see how much we can do today. All right, so you go ahead and tell me the type right here. What do we have for speed? What type of quantity is this? A vector quantity or a scalar quantity?
Scalar.
All right, so speed is a scalar. And for distance?
Vector.
Again?
Vector quantity.
No. All right. Distance is also a scalar. Scalar. Displacement, on the other hand, is a vector quantity. So I'll include this into our table here. All right, what about time? Is time a scalar or vector quantity?
Why?
Is time a scalar or vector quantity?
So for them,
No. Remember, you don't need to write notes. All right. If you want to, you can go ahead and write them. Anybody want to guess scalar or vector?
Yeah.
All right. So scalar. Now, what about temperature?
Vector.
Mm-hmm. What about temperature? Is temperature a scalar or vector quantity?
Vector quantity.
No, it's also a scalar.
Scalar.
So scalar essentially only has size, right, or magnitude. And then when you're talking about vector, you take into consideration both size and magnitude. Magnitude are size and direction, yeah, for vector quantities. And what about volume? Is volume a scalar or vector quantity?
Scalar.
Vector.
And density? What is density? Scalar or vector?
Scalar.
And frequency?
so scalar.
All right. And what about force?
So force is
Vector.
vector.
All right. So vector. And what about weight?
So weight a vector too.
So weight is also a vector. And we said this is already scalar.
And speed a scalar, so.
Exactly. All right, so we can move on then. So a scalar quantity is any quantity in physics that has magnitude only. So the number value, right? If you're looking at temperature, you would only have 10 degrees Celsius. So 10 degrees, 10 is the number value with units would be over degrees Celsius, right? So these are some of the examples. We have scalar examples of scalar with the speed, right? You only take into consideration the magnitude and your units, but distance as well, 25 meters. and for age, right, just 16 years. So you're not really considering the direction, right? While vector quantity is any quantity in physics that has both magnitude and direction. All right, so we see some vector quantities coming out here. What does X represent? What do you think X represents? We just mentioned it here, right? What is this? Have you ever seen this before? Or heard about it? Yes, no. Have you ever heard about displacement?
Yes, sir.
Exactly, displacement. So displacement considers both magnitude and direction. Let me see if I can squeeze it here. Displacement. All right, and what is V? What does this V represent?
Sir, vector, sir.
All right, what quantity? Not vector, what quantity? I've seen V before, right?
Volume.
Oh, volume is a big V.
Sir, velocity.
Exactly, velocity. So, velocity. Just for reference, in the exam, within an exam, I see this. This is velocity, while the big V is your volume. All right. Big V, capital V is volume, small v is velocity. And what is A here?
Acceleration, sir.
All right, so acceleration. And the F.
Force.
All right, very easy stuff. So we're not going into the higher things as yet. We're just completing the basics. Morning. So some of these, right, we said are some examples: velocity, acceleration, force, and we of course consider both the magnitude and direction. So you have 35 meters per second north, 10 meters per second squared south. This would be for acceleration. And you have a force going 20 newtons east. So an arrow above the symbol illustrates a vector quantity. It indicates the magnitude and also direction. So if you see this, right, this is indicating that it's a vector quantity. And you can also use the arrows to state the direction. But most times we usually just state north, east, west, or south just to avoid any confusion. And so is this clear for everyone? Anybody doesn't understand what is happening here?
Sir.
Mhm. Question? Johnson, have a question?
No, sir. I only say yes, sir.
Okay, okay. Anyone doesn't understand? Let me see here.
No, I don't, sir.
Go again, Alan, I didn't hear.
I don't understand.
You don't understand?
No, sir.
Where exactly you don't understand?
My tablet audio wasn't working well, so I didn't hear it, and it just coming back. So.
Oh, well, we have just been talking about the difference between scalar and vector quantities. We brushed on it in the past, but we didn't go in details. Now we intend to go in details, and we said that a scalar quantity it just has magnitude, right? Just has magnitude. While so you're just looking at the number, right? Which would talk about the magnitude and then the units. That's it. That's it for scalar quantity. For vector quantities, right? It is magnitude and direction. And these are just some examples of magnitude of vector quantities. Sorry. So you're looking at the magnitude, which would be your size, the direction, right? And of course, you have to include the units as well. So you have, this is the magnitude section, and this is the direction, right? Is that a little clearer?
Yes, sir.
All right. All right, so we'll move on now to addition. So whenever we're adding two vectors and they point in the same direction, right? Whenever there are two vectors and they're basically in the same direction, we simply add them. So a man walks 46.5 meters east, then another 20 meters east, right? This is distance or displacement. Which one would this be? Displacement or distance?
So this one,
No, right? Remember, we have the magnitude here and then the direction. So which one it would be? Distance or displacement?
so displacement.
All right, displacement. So we have the mag and we have the direction. So calculate his displacement relative to where he started, right? So essentially he started here. From this point, he walks east in this direction, right? Sorry, walks east, 46.5 meters east, and then he stops, he buys a bag juice, and then he continues 20 meters east even more, right? So if you can realize the difference between the size of this one and the size of this one, you can realize that?
Yes, sir. The red
Yes.
one longer.
Exactly, because it shows that he's walking much longer. So whenever you are displaying vectors, I need to see that that if you're having 5 newtons and then you have 10 newtons, the 5 newtons must be 2 times smaller or a half. So 10 newtons, let's say, look something like this, right? Your 5 newtons should look something like this, right? So you see the difference in size. Now they're both moving in the same direction, so therefore we go ahead and add them. All right, what would we get for this?
66.5.
All right, so in all you would get 66.5 east. All right. So magnitude relates to the size of the arrow, while direction, right, relates to the way the arrow is drawn. So, of course, they're moving in the same direction east. You have to represent that, and also the magnitude of 66 is bigger than the magnitude of 46 and 20. So basically, that this particular arrow would have to be bigger. So, is this clear for everyone? Right?
Yes, sir.
Yes, sir.
Who doesn't understand? Who is lost so far? Let me see. Nika, are you okay? Right?
Sir?
Are you okay? You understand?
Sir, I'm not fully on.
I just asked if you understand, if everyone understands. You should have stated that. Where don't you
Sir, I'm
understand?
never there here, sir.
You weren't hearing?
No.
Where?
Medially see part when you say 46.5 at displacement, but we don't know what else you have to talk about after that.
All right, so if you're not hearing, you can say, sir, can you repeat that next time? All right, so tell me now, Renika, which one of these would be bigger, the 46.5 or the 20? Which one of the arrows would be bigger?
Sir, 46.5.
Exactly. So whenever you're presenting magnitude, you should take that into consideration. The size of the arrow when you're presenting vectors, and when you're adding them, since they're moving in the same direction, right? Moving in the same direction, then you could just simply add them. All right.
Sir,
Go ahead.
so what if they're not moving in the same direction?
All right. That's what we're going to do next. I just want to ensure that we are clear on this. All right. Okay. Good. Let's continue. All right, so subtraction. So when two vectors point in opposite direction, you simply subtract them. All right, so a man walks 46.5 meters east and then he walks 20 meters west. So calculate his displacement relative to where he started. Of course, you would represent this by starting at where you began. Then you would draw the vector 46.5, right? And then you would place the tail of the second vector to the tip of the first vector, right? You place it relative here. It should be at the same distance. And then you would represent your 20 meters moving west. All right. Now I call this tip and tail method, right? This is the easiest way. So you would place the first, you would place the tail of the second vector, right, in line with the tip of the first vector, and then you represent these two. And of course, what is the displacement of this person? What would you get?
26.5.
All right, 26.5, you simply subtract them. So is this clear? All right.
I just came.
Okay.
I just joined the class.
You just joined the class? Well, let me see. We won't be able to go over everything, right? But we're just doing scalar and vector quantities, right? I've done this before. This should be very easy. But we're just talking about the addition. That's what we just did a while ago. And we said that if two vectors are in the same direction, you simply add them. Very simple. So if you have 46.5 here and you have 20 here, you add them, you get 66.5. And if they are moving in opposite directions, right, you simply subtract them. Right, this is simple stuff. So nothing too hard so far.
Okay.
All right. Now we'll go now to where it's getting interesting, right? I really advise you to pay attention. Right. So when two vectors are perpendicular to each other, you must use the Pythagorean theorem. Has anyone ever heard this before? Pythagorean or Pythagoras?
Yes,
No,
sir.
sir.
Yes, sure.
All right.
So that one think me about this sir.
Pythagorean theorem.
All right. So do you remember it? Like you
Sure, me
remember?
here not much sure when I deal with triangle.
And I didn't know triangles. All right. Good. You know how to represent it, or you know the formula?
Sure, A plus B equals C, something like that, sir.
All right. So let's say this is your
Word.
triangle. Let me see. How can I draw this? The best way. All right. Essentially, if you want to find this distance here, right? I will explain it. But if you want to find this distance, and let's say this is A, this is B, and this is C, A squared plus is equal, sorry,
Sir, A squared plus B squared equals C.
Right? It depends on which one is your, as I said, I explained it, but let me just introduce you to it. It will be A squared equal B squared plus C squared, right? This is the original formula, right? I'll go ahead and explain it now. So for example, a man travels 120 kilometers east. Just bear with me for a second. Then 160 kilometers north, right? Calculate his resultant displacement. So first he goes east, then he goes north, right? So he starts at this point, he goes east, right? Then he goes north, essentially, right? So therefore, the resultant vector or the displacement, what I think would be the displacement? Let me draw A, B, C. Or no, let me, which one of the lines do you think is your final resultant? So let me say A, B, and C. Which one is the final resultant?
A.
Exactly. So A would be a resultant. So you would draw the line from the tail of your first vector to the last point. All right. So let me go ahead and represent that now. All right. So first he goes 120 kilometers east. 120 kilometers in that direction. Then he goes 160 kilometers north. So we realize that this one is actually longer than this one here, 120 kilometers. Then we want to find a final displacement. So therefore we connect the place where he starts, connect the place where he starts to the place where he finishes. That is the final displacement. The distance between these 2 points would be your final displacement. So this is where he starts, and this is where he finishes. So as I said, we will connect the place where he starts to the place where he finishes. Just like that, right? This is where he started, this is where he finished. So this, we call this your horizontal component. We call this your horizontal component, and then of course we call this your vertical component. So the horizontal component would be X or Y. Which one would it be?
X.
All right, so the horizontal component would essentially be X, and your vertical component would of course be Y. All right, so is this clear so far?
Yes, sir.
All
No,
right.
sir.
No?
No, sir.
All right, let me go over it again. Now, a man travels 120 kilometers east. 120 kilometers east, then he goes, after he finishes at 120 kilometers, then he goes north. So we must calculate his final displacement. Let's go ahead and calculate his final displacement. So let's do that now. He goes 120 kilometers east. First, he starts here, then he stops and make a turn north. He goes north then. So if we realize that 160 is much bigger than 120, right? So we would have to represent that on as vectors. The red one, of course, is shorter than the 160. Then in order for us to represent this final displacement is the difference or the distance between where he starts to where he finishes. That is the final displacement. Now, you would make a annotation from where he starts, right? And then you would connect that to where he finishes.
Sir,
Go ahead.
you can tell the person who have their microphone on to mute their mic, please.
All right, I will monitor that much better. And there's noise in my background
Just
because I'm
mute
at school.
everybody.
I'm at school now, so maybe you're hearing my background.
Oops. Morning, sir.
My name is McIntosh.
You're going to use this room?
You're gonna use it?
You have a class?
Yeah, I have a class.
Oh, that's fine. I just want to know the rooms that they have. They said that the first one. I didn't know you were here.
Oh,
Oh,
because they cleaned it.
Huh?
Because I'm realizing that they cleaned it. All right.
Yeah, man,
I only
that's
have
fine.
one class. I only have one class. This one here that I'm in. So
Oh.
yeah, I can move to the computer room afterward.
Okay.
Yeah. So sorry about that. You would go from where he starts, and then you would continue to where he finishes. Now, this is where he finishes. So you would connect the start to the finish. And then this is your final resultant displacement. All right. Is that a little better?
So, sir,
Yes,
don't you
sir.
calculate?
Go ahead, Alan. I'm not hearing you.
Can you calculate anything?
Yeah, so we go ahead and do the calculation now. But
Yeah.
I want to ensure that we understand this particular section. All right. All right, so if this is a displacement, what do you think is the distance? What would be the distance? All right, so let's say this is a displacement. Let's say, for example, this is 100. Just for argument's sake, it's not actually 100 because we haven't done the calculation as yet. But before the time runs out, what do you think is the distance that he travels in all, the total distance he travels?
Yes.
Yeah, you can go ahead and throw it out.
160. Yes.
160?
160.
Sorry,
160.
160 plus the 120, sir.
Exactly. So his total distance would be 160. Total distance 120 plus 160. So this is a total distance, but the displacement is the position between where he starts, the difference in where he starts to where he finishes. All right. So as we said, that is a horizontal component, and this is a vertical component. So we'll pause and come back as quickly as possible. All right, so that we can finish this up for today. We can finish this Pythagorean theorem today. All right.
Yes, sir.